Hello friends, I welcome you in lecture number 4 on elementary analytic functions. In earlier lecture we have defined logarithmic function and its properties were discussed. Today we are going to discuss some examples on how to find out logarithmic function or logarithm of a complex number. So before going for examples, we just recall the definition of logarithm of a complex number. So if z is any non-zero complex number, natural logarithm of z is denoted by ln z and is defined as ln mod z plus I into argument of z. So we require absolute value of z and argument of z to decide the natural logarithm of z. So we will use this definition throughout this lecture. So let us start with example number 1. Here we are given some complex numbers and we have to decide their natural logarithm ln z as well as principal value of natural logarithm denoted by capital ln z. So we start by first complex number, it is 1. Before that again we write definition of ln z is log mod z plus I into argument of z, and it is defined for every non-zero complex number. So first complex number given is 1. So we start by taking z equal to 1. So as we know, z equal to 1 is on positive real axis, and it is obvious that absolute value of z equal to 1 is 1, and because z is on positive real axis, angle made by vector representing z is 0 with positive x-axis. So therefore argument of z, that is argument of 1, is nothing but 0 plus 2n pi, where n is any integer. To include all possible values of argument of 1, we are adding 2n pi. So argument of 1 is nothing but 2n pi, n is any integer. So now we have absolute value of z and argument of z, so we put them in the definition. By definition, ln z is ln mod z plus I into argument of z. So z is 1, so we write ln mod z means modulus of 1 is 1 and argument of z is 2n pi. So here we write I into 2n pi. N belongs to z. Now this is natural logarithm of 1 as a real number. So this is a real logarithm, and we know that real logarithm of 1 is 0. So this is 0 plus 2n pi I, n belongs to z. So finally we obtain log of 1, if we consider 1 as a complex number, is 2n pi I, n belongs to z. So you can see there are infinite number of values for the logarithm of 1 if we consider 1 as a complex number. So as we know that logarithm of complex number is multiple valued function, so it is justified here. Logarithm of 1 has infinite number of, so depending upon different integer values of small n, we will have different values of log 1. For example, if I take n equal to 0, one value of log 1 is 0. If I take n equal to 1, it is 2 pi I. If I take n equal to 2, it is 4 pi I. For n equal to 3 it is 6 pi I, and so on. Similarly, if we take negative 1, we will have minus 2 pi I. For n equal to 2, minus 4 pi I, minus 6 pi I, and so on. So there are infinite number of values for the same complex number 1. Now among these values we have to find out value of logarithm which is corresponding to principal logarithm, because we are asked to find out principal value of log z also. So if we concentrate here, then principal argument of 1 is 0. The principal argument of complex number is that value which lies in open close interval minus pi to pi. So here 0 lies in this interval. So principal argument of 1 is 0. So if we want to write down principal value of logarithm of 1, then it is ln mod z plus I into principal value of argument of z. Here z is 1, so it is ln mod 1 plus I into argument of 1, principal argument of 1. So therefore principal logarithm of 1 is log 1 plus I into 0, and that is log 1, and this is natural logarithm, so it is 0. So therefore principal value of logarithm of 1 is 0. So this matches with real logarithm. We know that value of logarithm of 1 as a real number is 0. So this is matches with principal value of logarithm. So in this way we just have to remember these two definitions. If we are interested in principal value of logarithm, here we are using principal argument of z, and for general logarithm we are using general argument of z. Next one is z equal to minus 1. So we find out natural logarithm of z equal to minus 1. Now we can directly write down ln minus 1 is by definition ln modulus of minus 1 plus I into argument of minus 1. This is nothing but ln 1 plus I. Now minus 1 is on negative x-axis somewhere here. So we have to measure the angle made by this vector with positive x-axis. So this is positive x-axis, and we can see this angle is nothing but pi. So here we can write general argument of minus 1 as pi plus 2n pi. To include all possible values, we write in this way. N belongs to z. Now log 1 is 0. This is real logarithm, and here we can take pi common, and this we can rewrite as 2n plus 1 pi I. N belongs to z. So it is nothing but 2n plus 1 pi I. N belongs to z. So we find out general logarithm of minus 1 is 2n plus 1 into pi I. N belongs to z. Now if we are interested in principal logarithm of minus 1, then it is simply this remains as it is, logarithm of modulus of minus 1, but instead of general argument we have to use principal value of argument of minus 1, and we can see the angle is pi, and pi is allowed as a principal argument. So principal argument is pi, and log 1 is 0, so it is pi into I. So therefore principal argument of -1 is pi into principal logarithm of -1 is pi into I, and this is general logarithm of -1 having infinite number of values depending on different values of integers. ln -1 is 2n plus 1 into pi I and belongs to z. Sorry, I have to rewrite this. ln -1 is 2n plus 1 into pi I and belongs to z. Okay, so we can denote in this way. The third one is z equal to -4. So it is similar to this one. Instead of -1 we have -4. So -4 will be somewhere on negative x-axis. So this angle is going to remain same. Angle made by this vector with positive x-axis will be pi. The only difference will be absolute value of -4. So let us do this also. Z is -4. So ln -4 is by definition logarithm of absolute value of -4 plus I into argument of -4. Absolute value of -4 is 4, and this is pi plus 2n pi. So because -4 is also on negative x-axis, so angle made with positive x-axis is pi. So argument is pi plus 2n pi. This is ln 4 log of 4 as a real number, and this we can write as 2n plus 1 pi I and belongs to z. If you wish, you can use scientific calculator to decide this ln 4 and you can put its values. Here I am leaving it as it is. So this is general logarithm of -4. Now for principal logarithm, here we have to replace by capital ARG. So by definition of principal logarithm, log of modulus of -4 plus I into principal argument of -4, which is pi here. Pi is allowed as a principal argument. So this is nothing but ln 4 plus pi into I. So therefore principal argument of principal logarithm of -4 is log 4 plus pi I. Log 4 is a real number. This 4 is considered as real number here. So in this way you can decide the general and principal logarithms of any complex number. Fourth one is I. So we take z equal to I. The complex number I is on positive y-axis. Suppose somewhere here. So we require this angle made by this vector with positive x-axis, which is pi by 2. So principal argument will be pi by 2 and general argument will be pi by 2 plus 2n pi. So by definition, log of I equal to log of absolute value of I plus I into argument of I. Absolute value of I is 1 and general argument of I is pi by 2 plus 2n pi, n belongs to z. And here log 1 is 0, this is real logarithm, and here we can take pi common, so it is 1 by 2 plus 2n into pi into I, or we can rewrite this as 4n plus 1 divided by 2. This we can write with this, but here we have taken 2 as LCM. And for principal logarithm we will just replace this small arg by capital ARG, and this notation is capital L, keep in mind, for principal logarithm. So here log of absolute value of I into I into principal logarithm of I. Absolute value of I is 1 and principal argument of I is pi by 2, and because log 1 is 0 we have pi into I over 2. So principal logarithm of I is pi into I divided by 2. Similarly, you can decide the logarithm of minus 4i. This I am not doing. Minus 4i will be somewhere on negative y-axis, so you will require its argument. So either you can measure counterclockwise, we have to measure this angle made by this vector with positive x-axis. So either we can measure counterclockwise or we can measure clockwise. So it is better to measure clockwise because this angle is going to be negative of pi by 2. So it will work in both the cases, for general as well as principal logarithm. This angle is going to be 3 pi by 2. So principal argument of minus 4i is going to be minus pi by 2, and the general argument we can write as minus pi by 2 plus 2n pi. N is any integer. So it is better to find out principal argument of a complex number whenever we are dealing with general and principal logarithms, because this principal argument is going to work in both the cases. And if you wish, you can write argument of minus 4i as 3 pi by 2 plus 2n pi also. Okay, so that is your choice. You can write any of these two, both are correct, but principal argument is always minus pi by 2 for minus 4i, because we require the angle which is in between minus pi and pi. So using these values of argument of minus 4i, you can easily find out general logarithm of minus 4i as well as principal logarithm of minus 4i. So I am not doing this, it is for homework. Next one is 1 plus I. So we try for 1 plus I. Z is 1 plus I. So 1 plus I, what is the location of 1 plus I in xy plane? So if you are familiar with the formula, if theta is the argument of z, then we know that tan theta is y divided by x, that is imaginary part of z divided by real part of z, which is 1 here. So the value of theta for which tan theta is 1 is pi by 4. Okay, so this complex number is in first quadrant, and the vector representing this complex number, this complex number is 1 plus I, and the angle made by this vector representing 1 plus I with positive x-axis is pi by 4. So therefore argument of 1 plus I is nothing but pi by 4 plus 2n pi, n belongs to z, and absolute value can be easily find out by the definition. Absolute value of 1 plus I is nothing but square root of real part square plus imaginary part square. So this is going to be square root of 2. Now by definition, ln z is nothing but ln mod z plus I into argument of z. Here z is 1 plus I, and we find that absolute value is under root 2, and argument of z is pi by 4 plus 2n pi. We must write n is in the set of integers, and therefore this we can rewrite as this is ln 2 raised to 1 by 2, and if we take pi common, this is 1 by 4 plus 2n. Pi is taken outside the bracket, n belongs to z. Now this is real logarithm, so we can write this as 1 by 2 into ln 2, and we keep this as it is. If we wish, we can take LCM, but here we keep it as it is. So therefore general natural logarithm of 1 plus I is given by this 1 by 2 ln 2 plus 1 by 4 plus 2n pi I, n belongs to z. Now for principal logarithm, we just have to replace this small arg by capital ARG, and here angle is in the interval minus pi to pi, so this will work as principal argument of 1 plus I, and absolute value is under root 2. So principal logarithm of 1 plus I equal to log of absolute value of 1 plus I plus I times principal argument of 1 plus I. Absolute value we had find out, it is under root 2 plus I, and angle is pi by 4. So this is nothing but 1 by 2 log 2 plus pi into I by 4. So log principal logarithm of 1 plus I is 1 by 2 ln 2 plus pi I by 4. So it is easy to find out logarithm of a complex number if we are familiar with absolute value and argument of a complex number. If you are not familiar for argument of a complex number, you can watch my lectures on complex numbers. Next one is 1 minus I. So we concentrate on that, how to find out logarithm of 1 minus I. So say z equal to 1 minus I. So if you observe, 1 minus I means x is positive and y is negative. So suppose this value is 1, so this is minus 1. So this is nothing but 1 minus I. Now to find out argument of this complex number, if you recall, we have discussed how to find out argument of a complex number. First you consider real and imaginary parts as positive. So we have 1 plus I. If I consider real and imaginary parts of this complex number as positive real numbers, then I can write my complex number as 1 plus I. Now argument of this complex number, as we discussed in previous example, is pi by 4 because it is in first quadrant. 1 plus I is in first quadrant, and we find that this angle is pi by 4 as we discussed in the previous problem. Now this 1 minus I is in the fourth quadrant, so this angle is also pi by 4, but if we measure in this direction, it is clockwise direction, so we have to write down minus pi by 4. That means argument of 1 minus I is minus pi by 4 plus 2n pi, and principal argument is minus pi by 4. If we wish, we can measure in this direction also. So in that case, it is going to be 2 pi minus pi by 4, because this angle is pi by 4, so this is also pi by 4, or the whole angle is pi by 4 and we are interested up to this, so we have to subtract this pi by 4, so it is going to be 7 times pi by 4. So if you wish, you can write 7 pi by 4 as a argument of 1 minus I, or if you wish, you can write argument of 1 minus I as minus pi by 4 plus 2n pi also. So once we have the argument, then the half work is done. It is not hard to find out absolute value of the complex number. So here z is 1 minus I, and from this discussion I can write argument of 1 minus I is minus pi by 4 plus 2n pi, n is any integer, and for understanding we write this also, or we can write argument of 1 minus I as 7 pi by 4 plus 2n pi, n belongs to z. So you can use any of these two. Absolute value of 1 minus I is square root of real part square, which is 1 square. Imaginary part is minus 1. So if you simplify, you will obtain square root of 2. Now by definition, log of 1 minus I is nothing but log of absolute value of 1 minus I plus I into argument of 1 minus I. So absolute value is under root 2, and here we can use any of these two, minus pi by 4 plus 2n pi or 7 pi by 4 plus 2n pi. So I am writing minus pi by 4 plus 2n pi, n belongs to z, and this we can rewrite as 1 by 2 log 2. We can take pi common, so this we can rewrite as 2n minus pi by 4 multiplied with pi into I, n belongs to z. So this is general logarithm of 1 minus I. For principal logarithm, we have to consider principal argument as minus pi by 4, and absolute value is same, 1 by 2 into ln2. So principal argument is going to be principal logarithm of 1 minus I is nothing but 1 by 2 ln 2 and minus pi by 4 into I. Okay, instead of plus 2n pi, we will just write down minus pi by 4. If we replace this small argument by capital argument, that is principal argument. So log root 2 plus I into minus pi by 4, that is minus pi I by 4. So in this way we can decide general logarithm as well as principal logarithm of any complex number. We just have to remember the definition of logarithm of a complex number, which is ln z equal to ln mod z plus I into argument of z. So I am not doing these two problems. You can similarly find out their logarithms using the method which I just discussed. Here in number 8, the complex number is z equal to 1000. So that means z is a positive real number and it will be on positive x-axis. So argument is going to be 0 and absolute value is 1000 itself. So using that absolute value and argument, you can write down the natural logarithm of 1000. This is similar to this one. You can find out argument using the expression tan theta equal to y by x, and then using the modulus you are able to write down the logarithm of complex number. Now we consider one more example related to logarithm of a complex number. So as in the case of real logarithm, in real logarithm we have this property, log of m raised to n equal to n into log m. This is true for real logarithm. But for complex logarithm, this property is not always true. So we will consider the example which will show that this property is not true for complex numbers. So our next example is on this property. This property is not true for complex logarithms. So why it is not true, that we discuss with this example. So here we can see we are asked to prove that the set of values of log of I square is not the same as the set of values of 2 log I. So as we know, logarithm of complex number is always having infinite number of values. So suppose I have in one set I have values of all the possible values of log of I square, and in another set suppose I have all the possible values of 2 into log I. So here we are asked to show that these two sets are not equal. So two sets are equal if they have same number and equal number of elements, or two sets are equal if A is subset of B and B is subset of A. That is, each element of A is again an element of B and vice versa. So here we are asked to show that the set of values of log I square, that is capital A, is not the same as the set of values of 2 log I, that is capital B. So that means we have to show that there is at least one element in one set which is absent in the another set. So first we will find out the all possible values of this log of I square, and then we will find out all possible values of 2 log I, and we will be able to show that these two sets are different. So we start by definition. Now log of I square means log of minus 1, which is by definition ln absolute value of minus 1 plus I into argument of minus 1. As we know, absolute value of minus 1 is 1 and argument of minus 1 is going to be pi, as we just discussed in previous example. Minus 1 is somewhere on negative x-axis, so angle made by this vector representing minus 1 with positive x-axis is nothing but pi. So here we have to write pi plus 2n pi to include all possible values. Now this ln1 is real logarithm, so it is 0, and here we can write 2n plus 1 pi into I, and each value depends on the integer z. So log of I square is nothing but 2n plus 1 pi into I. So therefore the set of values of log I square is, suppose the set is denoted by capital A, so here we can write 2n plus 1 pi I, n is any integer. So we can write sum of the values. Suppose I take n equal to 0, I will obtain pi into I. For n equal to 1, I will have 3 pi I. For n equal to 2, I will have 5 pi I, and for n equal to 3, I will have 7 pi I. Similarly, for n equal to minus 1, for n equal to 0, it is pi I that we have written. So for n equal to minus 1, it is minus pi into I. For n equal to minus 2, it is minus 4 plus 1, that is minus 3 pi I. For n equal to 3, it is going to be minus 5 pi I, and so on. So I am not writing all the possible values. This is just for understanding that these are the possible values of log of I square. So now we consider another part, the set of values of 2 into log I. So 2 into log I, before writing 2 into log I, we first find out what is log I, and then we will multiply with 2. So this is by definition log of absolute value of I plus I into argument of I. I means it is on positive y-axis, so this angle is going to be pi by 2. So argument is pi by 2, and absolute value of I is 1. So here I can write this as pi by 2 plus 2n pi, n belongs to z. Now log 1 is 0, and here this we can rewrite as, if we take LCM, it is 2 into 2n, that is 4n plus 1 into pi I divided by 2, n belongs to z. So this is log I. So therefore from this we see that if we multiply both sides by 2, we have 2 log I equal to 4n1 plus 1 pi into I. N is any integer. So therefore we can write this set of values of 2 log I. Of 2 log I is, suppose the set is denoted by capital B. So here we write 2 log values of 2 log I, that is we have to write 4n plus 1 into pi I. N belongs to Z. So if we write sum of the values for different values of integer n, suppose I take n equal to 0, I obtain pi into I. For n equal to 1, I will obtain 5 into pi into I. For n equal to 2, I will obtain 9 pi I, and so on. For n equal to minus 1, I will obtain minus 4 plus 1, that is minus 3 pi I. For n equal to minus 2, I will have minus 8 plus 1, which is minus 7 pi I. So this is the set of values of 2 log I, and it is denoted by capital B. Now if we concentrate on two sets A and B, the set A is minus 3 pi I, minus pi I, pi I, 3 pi I, and so on. So here you can see here 3 pi I is present in capital A, but it is not present in capital B. Okay, so 3 pi I is in capital A, but 3 pi I is not in capital B. So this shows that these two sets are not same. So I cannot write A equal to B. So the set of values of log I square is not the same as the set of values of 2 log I. To show that two sets are different, it is enough to show that one element is present in one set and it is absent in another set. So in this way we can have the idea that that property of real numbers log of m raised to n equal to n log m. This is not true for complex logarithmic function. This is true for real logarithmic function, and here we have seen that ln I square and 2 ln I, both the sets are different. So this is all about examples on logarithmic function. I hope you like this lecture. Thank you very much.